Here, beta, our topic is simple microscope. Our topic is simple microscope. This is what simple microscope. So, what is microscope? This is a device which is used to increase the angle of vision. This is a device which is used to increase the angle of vision. Which is used to increase the angle of vision. Increase the angle of vision. But I think all of you see, now you see the near point of our eye is called 25 centimeter. So without the lens, if you are observing this body AB, without the help of lens, with your naked eye, then what is happening here? You are observing this body at 25 centimeter. Now the size of this body appears to you, the angular size of this body appears to you alpha. And the value of this alpha is very small. So 10 alpha is, we will write any angle in terms of 10 alpha. So what is the angular size of this body with the help of naked eye? Alpha is the angular size of the body. Angular size of the body with the naked eye. We are not using here any lens. We are just observing this body without the help of any optical device. So this angle is alpha, and this alpha can be written as P by B. What is P? AB. Because this angle is very small, and you know smaller angle is measured always in terms of arc length upon radius. That here we are taking in terms of 10 theta. So angle of vision with the naked eye of this body is alpha, and 10 alpha is equal to P upon B. What is this distance? D. D is what? 25 centimeter. D is 25 centimeter. So you put this as equation 1. Now see here, beta, all of you. If you see the same object, but having bigger size, you want to see the microscopic bodies like the bacteria or any other things or a cell, then you use what? Microscope or very small things to see the very small size object. What you do? In case of simple microscope, you are using only one lens, and that is magnifying lens is convex lens. So to increase the angle of vision, what you do? You place another magnifying lens to magnify the image. We use what? We use single convex lens. Only one convex lens. If we are using only one convex lens, then that microscope is called simple microscope. Because you know convex lens is called magnifying lens. Concave is not. Concave is not magnifying lens. So in case when we are using only one convex lens, then the microscope will be called as simple. But if you are using more than two lenses, because if first lens, for example, if first lens magnifying the object by 10 times, then it's called simple. But in place of only single one, if we are using two microscope, its magnification 10 and another one is also 10. then total magnification will be 10 times magnified by this into 10 times magnified by this. That is 100. Now, if you are using four lenses, then if the magnification power of this lens is what? 9. If the magnification, this one is again 20, then what is the total magnification? Magnification always multiply. Why? Because whatever be the size of image that it magnified, it is further magnified by this, and the image formed by this lens is act as an object for third lens, and this third lens will further magnify the size of image. It means that the magnification goes on increasing, it multiplies. So that's why magnification always multiply. 10 into 9 into 20, this will be total magnification. 100 into 9, 900, 900 into 2, 1800, 18,000 times the total magnification. It means in compound microscope, not a single microscope is used. In place of single microscope, more than one. That is 2, 3, 4, 5, and whatever be the number of convex lens that we goes on increasing. The purpose is to magnify the size of image. Here we are discussing about the simple microscope. So see what happens when you are using only a single microscope. What we are doing, we are placing a convex lens. This is known as a magnifying lens. And we are, if the focal length of this convex lens, if the focal length of this convex lens is Fe. Why Fe? Because from here we are observing the object, not directly. We are placing the object here. And to magnify the size of image, we are placing the object within the focus of this lens. And that's why this lens is, this point is the focus point of this convex lens. Since eyes is just kept in front of this lens, that's why this lens is known as the eyepiece. Eyepiece. This lens is known as eyepiece. Now you see how the diagram will be formed. If this is the focal length, this will be again focal length. Here, this side, focal length. Now, this is what object. Now, draw the diagram, ray diagram of this image. Parallel, it will passes through the focus. One passes through the center, it will remain undeviated and most like this. These two are going apart. So this side they will never intersect. These two rays are entering on our eye, and due to this reason, these two rays are entering in our eye. So for our eye, this side, since these two refracted rays are moving away from each other. So for our eye, the image will be not from backside. If you produce it backward, just make it straight. So see here, beta. In this case, the virtual image is formed because the refracted ray not really cut. If we produce it backward, it appears that this refracted ray cut at this one. Now what you are observing, the image size magnified to image size is more than the object size. And the angle of vision increases because in the previous case, you were keeping the object here at 25 centimeter. And now here what you are doing, you are, see here, there may be two cases. If you place the object at the focus point, then what will happen? See here, this is the first case. When we are placing the object within the focus and we are observing the image at D, this is known as fine adjustment. This is known as fine adjustment. But during fine adjustment, we are observing the image of the object at D, that is least distance of distant vision. And you know, when we are observing any body at 25 centimeter, then we can observe that body very minutely, very clearly, with more accuracy. So that's why when we are observing the body at 25 centimeter, if the image of this body is observed at 25 centimeter, then this types of adjustment is called fine adjustment. Eyepiece during fine adjustment. Eyepiece during fine adjustment forms image forms image at D. Forms image at D. Now you see it, beta. This is the angle beta, and this is the object distance. Let this distance be UE. Object distance from eyepiece lens, UE. Now you see it, beta. For this lens, this is angle beta, and what is the angle of vision with the naked eye? It was alpha. So magnification here will be, here the magnification will be, all of you just observe this one. But I see here the magnification will be the ratio of angle of vision with the lens beta. But how many times it multiplies? It how many times it increases the size of image? Beta times. And what was the original angle? Alpha. This is known as angular magnification or simply magnification. Now here, what is the value of beta? AB by P by B. Again P by B. AB by UE. AB by UE. AB by UE. And you see here, one sign convention is there. All the distance measured in the direction of incident ray, we are taking always positive. Now this is the center. This is the origin. Optical center is the origin. For measuring the UE, we are moving in opposite direction. This is the origin. And this is the direction of incident ray. So this direction will be positive. But this one is the origin. Optical center is the origin. In case of mirror, pole was origin. So when we are measuring the distance from here, we have to move in opposite to the direction of incident. That's why this distance is minus UE. Similarly, in the previous case, D will be also minus Y because the object was here. We are moving like this. From I, we are observing this distance minus D. So, beta upon alpha. What is the value of alpha? AB upon minus UE minus D. So, beta, just revert this one. You will get what? Minus minus cancel out. So it will be D by M is equals to D by UE. D by UE. This is the first equation. And what is the value of beta? You write here beta is equals to AB upon UE. AB upon minus UE. You put this as equation second. Now here second by 1. We get magnification formula D upon UE. This is equation number 3. Now you see here, beta, for object length, because we have to represent magnification in terms of the focal length. Because how the magnification is related with the focal length of eyepiece, so we have to use lens formula. We have to use what? Lens formula. See here, beta, what is lens formula? For lens 1 by V minus 1 by U is equals to 1 by F. This is the lens formula. Now, where the final image is formed in case of final adjustment, in case of final adjustment, fine adjustment, in case of fine adjustment, in case of fine adjustment, fine adjustment. Image. Final image forms at D. It is minus D. Minus D. Where is the object UE? Minus. UE is minus sign. Minus UE is equal to 1 by F. Focal length of convex lens we take always positive. This side direction is positive. You should remember the focal length of convex lens is always positive, and for concave lens it is negative. When this lens is kept in air, that is the density, optical density of air is lesser than convex lens medium, that is glass. So see here, minus minus plus 1 by UE. We take this quantity right side, 1 by F, this is E, focal length of eyepiece. Minus sign goes this side, 1 by D. So see here, 1 by UE is equal to, take calcium, Fe D, to this side, D plus Fe. So beta see here, put this value 1 by U in equation third. Putting the value 1 by U in equation third. This is equation number third. Putting the value in equation third. Putting the value of 1 by U, 1 by UE in equation third. In equation third. Here, but our magnification is equals to D by UE in place of 1 by U. UE is in denominator. So we can write D plus Fe by DFE. But our DD cancel out. So magnification formula will be, we can write 1 plus D by Fe. See here, beta Fe plus D when we will take LCM. Same D plus Fe by Fe. So this is the magnification formula during fine adjustment. Magnification formula during fine adjustment. 1 plus D. D is what? Least distance of distinct vision. That's 25 centimeter. During calculation of magnification, you write everything in meter. D is 0.25 meter and focal length of eyepiece lens will be given to you. This is the formula for magnification during fine adjustment. Now, here we have in the case of what? The normal simple microscope during fine adjustment. That is image formed at D. And in this case, when you are observing any body, anything, or for example, when you're reading anything at 25 centimeter, you might have felt that there is more strain, more stress is there in your ciliary muscles of your eye, and you are feeling more stress. Whereas in comparison to that one, when you are observing, when you are watching a cricket match in any stadium, your eyes remain very relaxed one, and ciliary muscles is also remain relaxed. Now, so that type of adjustment is called normal adjustment. Normal means your ciliary muscles remain relaxed and final image forms at infinity. Now you see here, in case of normal adjustment. So in case of normal adjustment of what? Normal adjustment of simple microscope. During normal adjustment, final image forms at infinity. Final image forms at infinity. forms at infinity. Now all of you see, this is the convex lens. You know the ray diagram. This is the principal axis. This is the focus point of eyepiece. This is the focus point of eyepiece. Now you see, when we are placing the object here on the focus point of this eyepiece, you are keeping your eyes here. You are just watching this object. Now, when you are placing the object is at here, and you want to see the image of this object at infinity, we know that when we are placing any object at focus point of any lens, then we observe the image at infinity. Let's see the ray diagram. Parallel lines, it will passes through the focus, and the line which is passing through the center of curvature, no, this is called the optical center. This line will move in a straight line. So this line will move in a straight line, which is passing through the optical center. And the ray which is passing parallel to the principal axis, that is paraxial ray, after diffraction passes through the focus. Now what you are observing, these two refracted rays are going parallel. It means they will cut each other at infinity. And when you observe this body from here, you will see the image of this body here at infinity. Final image at infinity. Because the parallel lines cut at infinity. Final image at infinity. Now you see here, in this case, what is the angle of vision? Beta. And this length is what? Focal length of eyepiece. This length. Now, here the magnification beta will be AB by, we have to take this distance. From the optical center, this distance, we are not taking the focal length, we are taking the distance of object. So here the distance of object is focal point of eyepiece, P by B. Now you see here, this is the second equation. And what was our first equation? Angle of vision with the naked eye. That is, angle of vision with the naked eye is known as alpha, and this is known as AB upon D. This was our first equation. We have already discussed. Now, dividing equation 1 by 2. Dividing equation 2 by 1. Beta by alpha. Angular magnification. We call this angular magnification. So, AB by FE upon AB by minus D. AB by minus D. So what you are observing here, the formula of magnification is D by FE. Magnification is D by FE. But in the previous case, what we have observed, magnification formula during final adjustment was 1 plus D by FE. 1 plus. It means magnification in case of final adjustment, we are observing more than that of normal adjustment. This is the formula for normal adjustment. Normal adjustment. Now you see here, beta, all of you, we will discuss about compound microscope. This is a device which is used to see a very small object, and it uses more than 2 lenses. More than 2 lenses. This is a device which is used to see microscopic object. Which is used to see microscopic object, and it uses more than 2 lenses. More than uses 2 or more than 2 lenses. The lenses which are used for magnification, the lenses which are used in compound microscope for magnification are only convex lens. Concave lens are used also. Galileo used concave lens also. But that concave lens was for making the object erect, not for magnifying. Because with the help of concave lens, we cannot magnify any lens. In the ray diagram, we have already observed that one. No, you see here. So in compound microscope, they are at least in very simple, very simplified type of compound microscope, there are two types of lenses are there. There are two types of lenses. But the first one is objective lens. Objective lens. Objective. And second one is eyepiece. But the lens which is facing the object, this lens, the lens which is facing object, but this lens, इस लेंस को ऑब्जेक्ट के जस्ट सामने रखा जाता है जिसका इमेज बनाना होता है. So the lens which is facing object is called objective lens. What is the characteristics of this lens? See here, since the object is very microscopic one, object is microscopic one. So to see the object, we aperture of the lens should be small and its focal length should be small. To see the bigger object at large distance, just in opposite to simple compound microscope, in case of telescope, we have to observe the object at very large distance. So that's in that case, we will take the objective at very large aperture and large focal length. But in case of compound microscope, the object size is very, very smaller, microscopic. And that's why the lens which is facing the object should have a small focal length. What is the characteristics of this lens? Objective lens have a small aperture. Why small aperture? Aperture means size, diameter, linear aperture and angular aperture. I have already explained this one. The objective lens have a small focal length and a small aperture. In comparison to this lens, the lens which we are keeping in front of our eye, that is known as the eyepiece. The lens which is kept in front of our eye, which is kept in front of our eye, in front of our eye, is called eyepiece. What is the characteristics of this lens? What is the characteristics of this lens? This lens should have comparatively larger focal length, larger eyepiece. Because in comparison to microscopic body, our eye size, eyeball size is larger. And see, so that's why here in this case, the eyepiece should have, in comparison to this lens, eyepiece have large aperture and large focal length. Eyepiece have large aperture and large focal length. Eyepiece have large aperture and large focal length. Now you see, beta, all of you, how we can draw the diagram, ray diagram. And through that one, I will explain everything. In case of compound microscope, see here how. First, we will see the normal adjustment. Compound microscope during normal adjustment. During normal, and just we have discussed about normal adjustment that final image forms at infinity. Yes. See here, beta. This is object E. And we are keeping here a lens. Whose focal length is small. Now see here, focal length of this lens is smaller. This lens is kept in front of object. So that's why this lens is called. Now you see here. If this is the focal length of objective, FO for focal length of objective. FO is the focal length of objective. Now you see here. First, we have to keep the object in between F and 2F, closer to F. If we are making more and more closer to F, then more will be the magnification. See where we have to keep this object. We have to keep this object between 2F and F of the objective lens. This lens is called objective. Why objective? Because this lens is kept in front of the object. And where this object should be placed? By sliding, we adjust the position of this object between 2F and F. But for getting more magnification, one thing you remember, we have to move this lens closer to this to get more and more magnification. See here. A, B is the object. But as here, this is F, O, focal length, this is 2F. But all of you see, when we are keeping the object between F and 2F, image formed beyond 2F. Parallel passes through the focus, center goes straight, center it will go straight,